All right, welcome to our lesson on work, energy, and power. And first of all, have no fear. Although it looks long, there's many pages, there's not a lot of actual stuff, so we will get through here quite quickly. So first of all, a bit of a review about work. Work has to do with can you guess it? Yes, it's a force. Can't spell. A force causing a displacement, and it is measured in joules, Joules. Work is also known as the change in energy, something we haven't talked about and won't actually be coming today, but will be a little bit later, so we'll see that. There are basically two types of energy. You can divide it up. One type would be kinetic energy, Ke, or for kinetic energy. You can probably guess kinetic energy has to do with things that are moving. Okay, objects moving. The second type of energy here that we're going to cover today is potential energy. And there, within potential energy, we could even say, oh, there's a couple different types of potential energy. There is, for example, a gravitational. I'll just abbreviate that, gravitational potential energy. And there's another one called elastic potential energy. I'll just leave that. Now I'm only covering these three. The one type of kinetic energy, objects that are moving, and gravitational potential energy and elastic energy. Those are the only three in our course. There are others. Okay, we're just going to keep it a little bit simple here. And so today we're going to start off with the gravitational potential energy. Then this is the order that we're doing things today. We'll do that first. Then we'll be talking about elastic, and then we'll be talking about kinetic energy, and then we'll be talking about, the last but not least, we'll be talking about total mechanical energy. So first of all, what is potential energy? Energy that is stored. So we're going to say it is stored energy. You can also think of it being stored something because of its position or because of how it's shaped. Okay, the energy that is stored. There are two types I mentioned, gravitational potential energy and elastic. Can you guess which is which here? The gravitational potential energy, this would be this one right here. This would be an example of gravitational potential energy. This would be the elastic potential energy. I don't know if you watched the Roadrunner movies or I mean the cartoons when you were young, but some great little screen caps from there. So an object can have stored energy or potential energy because of its position, and I'm also going to say position in two ways, I guess. In the ways that we're looking at right now is because of its height. So this rock here, this is the object which has gravitational potential energy. It has the possibility of falling down and doing quite a bit of damage, and he's hoping that the Roadrunner is going to be at the bottom. I think he put some bird seed over there. You can also have an energy because of its position, thinking in a little bit more abstract way, because of the way it's shaped, okay, or the way something's been deformed. Normally, this bow, I guess, would look kind of more like this and wouldn't be pulled out of position, but because it's been pulled like that, there has been energy has been stored in this bow, and when he lets go, poof, he's going to be propelled forward, and he hopes to have the same speed as the Roadrunner. Let's take a look at the formula for this is the first one for gravitational potential energy. So PE is just general potential energy. What type of potential energy? Gravitational potential energy. It depends on only these three things. Its mass, the gravitational field strength, and the height. So here we're going to say PE grav is going to be equal to, I'm going to write it all out here. PE grav is gravitational potential energy. Oh, I'll just say E for that one. It is measured in joules. M is mass, which is measured in kilograms. G is the gravitational field strength. We'll be talking more about that gravitational field strength in a later unit. You're familiar with thinking of G as the acceleration due to gravity, so really it's two ways of describing the same thing. When I'm talking about G and I'm saying acceleration due to gravity, I usually say meters per second squared. Now I'm going to say newtons per kilogram. Okay, you'd be okay if you said meters per second squared, but this way is better in this situation. If I was dropping an object, I would want meters per second squared. In this place, I want newtons per kilogram. H is the height, and that would be measured in meters. So looking at this object over here, it would have some big mass, right? This would be the height. When we draw it from the center of the mass, this would be the height in meters. And of course, it looks like it's taking place close to the surface of the Earth, so G would be about 9.8 newtons per kilogram. All right, I'll turn to the next page now. A word about H. H has to do with the height. It doesn't have to be the ground. To determine the gravitational potential energy, so that's PE, grav, of an object, a zero height must be arbitrarily assigned. What does the word arbitrarily means? It means we get to pick it. Just like in the previous kind of questions with inclined planes and things like that, we would choose to say which way is positive or negative to be convenient. Here we can pick the zero level ourselves. Usually the ground is chosen. Okay, so usually we take the ground, but you could do other ones. So in this case, let's say that we're going to say that this is the zero level. Okay, so here's a person on a swing. They would have the maximum, if I was to number this, 1, 2, and 3. Where would they have the most potential energy? When they're highest. So at position 1, they would have the most potential energy. At number 2, they would have the least, and 3 looks like they're not all the way back up again, so they would have somewhere in between. Okay, so where does the person have positive potential energy? Well, actually, for all of them. How would we place this person to have zero potential energy? Well, if this is our ground, if the ground level is where we said, hey, let's make that zero, we would have to put the person on the ground, right? So we would say, where does a person have zero? On the ground. Where would they have negative PE? Well, I guess if we dug a hole and said, get down into that hole a little bit, then they would have a negative height. So below the ground. Okay, so most of the time we're going to pick an H that's the ground. Sometimes we might pick a different one to make things easier, but as long as we're consistent, it doesn't matter what we do. So let's try to do some stuff with some proportional thinking. If we say that, here's our formula again, and we say that PE and H are directly related. So if I were to double the height, so in other words, if I was to say like times 2 here, then what would happen if I multiply H on the right hand side and everything else stays the same? Overall, this right hand side would double, so therefore to keep things equal, this side would have to double. So in other words, the first question is what would happen to PE? PE is going to get multiplied times 2. What if we multiply the height by half? So here I'm going to say times a half. Well, then this is going to get multiplied by half. So PE would also get multiplied by 1/2. Using the same thinking, can you determine the blanks in this diagram? Well, here, and again, you've noticed that this is our zero level we've chosen, and because the PE is 0 when the ball is on the ground, and if it's 50 joules up here, and it looks to me like each of these steps is about an equal amount, so if it's 50 joules and there seems to be 5 steps on the way down, then this would go down each by 10. This would be 0. Now here's a question. If we took the ball and placed it in each of those stair levels, we've already figured out what these answers are going to be. Now, if we let the ball roll down on an incline, it's going to be moving pretty fast by the gets to the end. How much potential energy will it have on the bottom? The difference between this picture and this picture is on the one on the right, it's moving. On the one on the left, it's not moving. Well, let's think. PE, gravitational, has to do with its mass times the gravitational field strength times the height. Is there any velocity in that formula? No. Does it matter that it's moving there? No. So, in other words, this answer will also be 0 joules. Similarly, instead of having it roll down the incline, but we just dropped it, how much potential energy will it have? Its position is still at the 0 height, so it'll be m times g times 0, so it'll be 0. Okay, see how fast we're moving along? We're on the next page already. Okay, so we're moving now to elastic potential energy. So how far we've gone? So we've got energy, and then we've got PE, and we've done gravitational. Excuse me, I have to go let my cat in. I'll be right back. So we've done PE gravitational. Next we're going to do PE elastic, the second one, and then we're going to be covering kinetic energy. So just to keep along how far we've gotten, we've talked about this one. Now we're on our second one, elastic potential energy. So elastic potential energy is, again, it's stored energy, but unlike the previous one where it's stored because of its height, here it's stored because of the way it's been deformed. In this first example here, if I would imagine that if this person, and it looks a little uncomfortable over here, if this person wasn't pulling on those springs, then it wouldn't be the same length. It would probably be something sort of this length, right? But because it's been stretched, it's a bit more like that length. The amount that it's been stretched would be about that amount x. All right, so this x here would be the amount of stretch. And you need some stretch in order for something to be stored in that spring. Here we're talking about the compressed spring of a dart gun stores elastic potential energy. When the trigger is pulled, the springs apply a force. So I don't know if you can see inside of there, but before it's shot, it's very tight together. After it's shot, now the spring has sprung, and it's a longer one. So in this case, the difference here, again it would be x, but in this case, instead of x being the amount of stretch, it was compressed. Amount of compression. So elastic potential energy happens when a spring is either stretched or when it's compressed. And you know what? I'm not going to get too much into the formula yet because we're going to use this later. I just want you to start thinking about what elastic potential energy looks like. So let's look at this trampoline one here. It says, where is the greatest elastic potential energy? So where is there the most energy stored? Now this doesn't look like a spring, but I hope you can appreciate the trampoline, the fabric of the trampoline itself is being the spring. So where is the trampoline the most either stretched or compressed? And I would say the answer would be position number 1. Where is the greatest gravitational potential energy? What's gravitational potential energy? Remember that one? That one is the mgh. Well, it would happen when, well, the mass, I think we're talking about the person that's jumping all the time, the mass stays the same, the g is staying the same. So I guess the question is, when is the boy, I think it's a boy, when is the boy highest? So I think that would be this one, when they're the highest, because again, it doesn't matter where we pick our zero level. We could put our zero level at the trampoline, or we could pick at the ground, but clearly it'd be position number 3 where the person is the highest. Now we haven't even done KE yet, but what is KE? Kinetic energy, the energy because some object is moving. Where do you think the boy would have the greatest kinetic energy. In which position, number 1, 2, and 3, is he moving the fastest? And in fact, this is probably where he's moving the fastest. Here he's going upwards. Here he's probably not moving at all. It's at that lowest point when he's not moving. Here he's like just taking off, and that looks like his arms are out. He's having a good time. We should put a smile on him there. He's at his highest point. So I think that that would be at position number 2. So I'm going to save the formula for a little bit later and say we will be working with springs later. Moving along to the next page here, we've got a couple examples. The first one says a cart is being pulled at a constant speed along an inclined plane to the height of a chair. Can you make out that this is the chair? And that's the back of the chair. The first question is, what is the potential energy at the top of the chair? Well, remember we have two types of potential energy. We have our PE gravitational potential energy, which is at mgh, and we have the PE elastic. It doesn't seem to me like there's any spring happening here. So really, when we're talking about potential energy, it's got to be this PE grav. It's got to be that mgh. So maybe what I'll do is I'll just draw this a little bit easier. Let's say that the object starts at the ground and then later ends up at a certain height. Okay, so this is the height it's at. I'll just draw this height in. Notice it doesn't matter how much it moves horizontally. Really, we're only interested in what was its height. The mass of this object is 3 kilograms, g is 9.8, and the height is 0.45 meters. So our answer would be 13.23 joules, which really, with two significant figures here, this would really be 13 joules. Okay, now example number 2, it's the exact same situation. I just copied the diagram a second time. Now we're talking about the force. It says if a force of 14.7 newtons is used to drag. So here we've got this this object, and the force is 14.7 newtons, and the displacement is 0.9 meters. Okay, so that's the length of this diagonal over here. How much work was being done? How do you find work? Well, work is equal to F times delta D times the cos of theta. The work is 14.7 newtons. The displacement was 0.9. Now be careful about the angle here. I know we're tempted from our work with the inclined plane to say, hey, let's take the angle that's in the inclined plane. But the angle there is the angle between, the difference between the direction of the displacement and the direction of the force. And they are going the same direction. So it's going to be cos of 0 degrees. In fact, the cos of 0 degrees is just equal to 1. So it's just 14.7 multiplied by 0.9. And if you take the time to click that into your calculator, you'll notice that it is indeed that same 13.3 joules, which two significant figures would give us our 13 joules again. Very cool that it's the same amount here. So in fact, one way you could look at this, you could say work was being done on that cart, and that work added to the amount of potential energy it had. It took it from a place of lower potential energy to a place of higher potential energy. All right, we are in the last kick here. We're talking about kinetic energy, and this is the motion, the energy that something has because it's moving. Perhaps the only thing surprising in this one is that we have a half and a squared in there. So it's not just mass times velocity. It's pretty obvious that if it's the energy that something has, that its mass would be in there, because a more massive object moving would have more kinetic energy, and if it's moving faster it would have more kinetic energy. But perhaps the little bit of surprising thing is that 1/2 and the 2 in there. So just a reminder that KE is scalar, so despite the fact that it'll have motion in a certain direction, the KE is scalar. So even if it's moving downwards, we could say KE has a positive amount of energy. If we double the mass, we're going to do that kind of thinking proportionally again. If we double the mass, what happens to the Ke? So looking over here, if I was to say, okay, if I was to change this mass and just to double that, times it by 2, but keep everything else the same, then what's going to happen? My kinetic energy is going to get multiplied by 2. So the Ke will be multiplied by 2. What if we have the mass? Well, Ke is going to get multiplied by a half. Now here's a bit of a difference. We're gonna double velocity. So in this case, we're going to say, what happens if we just take now inside here, inside there. Now we're going to say, okay, what happens if I multiply that times 2? So instead of a v that's getting squared, it'll be a 2v that's getting squared. So what happens when 2v gets squared? Well, this entire side is going to get 4 times larger, right? Because this is 4v squared. So that will have an effect of making, when we multiply this times 2, that times 2 part gets squared. So this is going to get multiplied by 4. What happens to Ke? It's going to get times 2 squared, or we can say it's going to get multiplied times 4. What happens if we have the velocity? It's the same thing as saying times 1/2 squared, or it's going to get multiplied by 1/4. Okay, last one here, we're putting it all together. What happens if we double velocity? So just looking at our formula, Ke equals 1/2 mv squared. So we're going to double the velocity. So this part here is going to get times 2, and we're going to have the mass. What's going to happen? Well, our Ke from this part here is going to get multiplied by 2 squared, and it's going to get multiplied by a half because of that. So in other words, it's going to get multiplied by 4 times a half. So Ke is going to get multiplied by 2. All right, we're almost done. We got a few little example questions here. It says determine the kinetic energy of, this is just like a plug and jug kind of question, so I'll bring out our formula here. Ke equals 1/2 mv squared. The mass is going to be 625 multiplied by that velocity of 8.3 all squared. When I plug it in, I get 104, and there are some digits there, but I have to look at the fact that there are 3 significant figures. So I'll write it in scientific notation. I'll put 1.04 times 10 to the 5 joules. Okay. The second example, it says, what if we're moving with twice the speed? Then what would its new kinetic energy be? So since my velocity is multiplied by 2, it's doubled, and that's being squared on this side, my kinetic energy will be multiplied by 2 squared. So if I take my old answer, which was in my calculator not rounded, and multiply times 4, and then round it to 3 significant figures, I get 4.17 times 10 to the 5th. The last one, and I think we'll conclude this video and finish that other one on a different short video. It says, Missy DeWater, the former platform diver for the Ringling Brothers Circus, had a kinetic energy of 12,000 joules just prior to hitting the bucket of water. If Missy's mass is 40 kilograms, then what is her speed? So here it's the same formula, but what we're going to solve for is the speed, the v, instead of the kinetic energy. So I'll put in my 12,000 is equal to 1/2 times 40 times v squared. A half times 40 is equal to 20. Now when I divide both sides by 20, I will get 600. So v will be equal to the square root of 600, which is approximately 24.5 meters per second. Alright, I'm going to stop that now. I hope you have enjoyed this video, and we'll talk to you later.